Next, a step-by-step explanation of what is a power film capacitor is based on the below points. Film capacitors, plastic film capacitors, film dielectric capacitors, or polymer film capacitors, generally called film caps, as well as power film capacitors, are electrical capacitors with an insulating plastic film as the dielectric, sometimes combined with paper as carrier of the electrodes. It means these capacitors have multiple names: film capacitors, plastic film capacitors, film dielectric capacitors, or polymer film capacitors. They are commonly called film caps or power film capacitors in practical applications. They are a type of electrical capacitor, which means they store and release electrical energy in circuits. The main dielectric or insulating material used is a plastic film. This plastic film is placed between the capacitor plates or electrodes. Sometimes paper is added along with the plastic film. The paper acts as a support or carrier for the metal electrodes. This combination improves mechanical strength and layer stability. The dielectric films, depending on the desired dielectric strength, are drawn in a special process to an extremely thin thickness and are then provided with electrodes. It means dielectric films essential for capacitors are created by drawing a material to an extremely thin thickness determined by the desired dielectric strength. These thin films are then provided with electrodes to form a capacitor structure. The electrodes can be metallized directly onto the film or be separated metallic foil. The electrodes of film capacitors may be metallized aluminum or zinc applied directly to the surface of the plastic film or a separate metallic foil. It means the electrodes in film capacitors can be made in two ways. A thin layer of aluminum or zinc is coated directly onto the plastic film. This is called metallized film, or a separate metal foil is used along with the plastic film. These two conductive layers are then wound or stacked with the dielectric film to form the capacitor. Two of these conductive layers are wound into a cylinder-shaped winding, usually flattened to reduce mounting space requirements on a printed circuit board, or layered as multiple single layers stacked together to form a capacitor body. The simple meaning of the sentence is two metal coated layers are rolled up together into a cylinder shape to make the capacitor. This roll is often flattened to save space when placed on a circuit board. Sometimes, instead of rolling, the layers are stacked flat one on top of another to form the capacitor. Next, we discuss about the advantages of the power film capacitors. First one, high voltage and surge currents handling. In simpler terms, film capacitors can withstand high voltages and handle large surge currents, making them suitable for power electronics and applications requiring pulsed power. Second one, low ESR and ESL. In simpler terms, the low equivalent series resistance and equivalent series inductance minimize energy loss and heat generation, resulting in improved efficiency and performance in high frequency applications. Third one, excellent temperature stability. In simpler terms, film capacitors maintain their capacitance and performance over a wide range of temperatures, ensuring reliable operation in diverse environments. Fourth one, long lifespan and low failure rate. In simpler terms, film capacitors are known for their long operational life and low failure rate, making them ideal for applications where high reliability is crucial. Fifth one, non-polarized. In simpler terms, their non-polarized nature allows them to be used in AC circuits without the need for polarity considerations, simplifying circuit design and improving flexibility. Sixth one, high accuracy capacitance. In simpler terms, film capacitors can be manufactured with high precision capacitance values, crucial for applications requiring accurate energy storage and filtering. Next, we discuss about the disadvantages of power film capacitors. First one, larger size. In simpler terms, compared to other capacitor types like ceramics or electrolytics, film capacitors are bulkier for the same capacitance value, which may limit their use in compact circuits. Second one, higher cost. In simpler terms, the manufacturing process and materials used in film capacitors can contribute to a higher cost compared to other capacitor types. Third one, no self-healing. In simpler terms, unlike metallized film capacitors, some power film capacitors, especially those using foil, do not have self-healing properties, which can reduce reliability after dielectric breakdown. Fourth one, power energy density. In simpler terms, film capacitors store less energy per unit volume than electrolytic capacitors, making them less efficient for high capacitance energy storage applications. Next, we discuss about the applications of the power film capacitors. First one, power electronics. In simpler terms, power film capacitors used in inverters, converters, and switch mode power supplies for energy buffering and filtering. Second one, high voltage power systems. In simpler terms, power film capacitors ideal for high voltage DC and AC systems due to their insulation strength and stability. Third one, induction heating, plasma generators, and medical equipment. In simpler terms, power film capacitors employed in demanding applications where high frequency and high reliability performance is essential. Fourth one, motor run capacitors. In simpler terms, power film capacitors provide continuous phase shift and voltage support in single-phase electric motors. Fifth one, high voltage power factor correction. In simpler terms, power film capacitors improve power factor and reduce reactive power in large industrial and utility grids. Sixth one, audio circuits. In simpler terms, power film capacitors used in crossover networks and audio signal paths for their accuracy and low distortion. Seventh one, resonant circuits. In simpler terms, power film capacitors support high frequency oscillation with low loss, critical in tuned circuit designs. Eighth one, wireless electric vehicle charges. In simpler terms, power film capacitors enable efficient energy transfer and filtering in wireless power transfer systems. The image displays the internal structure of a metallized film capacitor. Highlight its key components. Wear, protective film and coating. This is the outermost layer, provides mechanical protection and insulation. Wear, metallization electrode. This is the thin layers of metal deposited on the plastic film serve as the electrodes. Where plastic film. This is acts as the dielectric material separating the electrodes and enabling charge storage. Where contact layer. This is connects the metallization electrodes to the terminals. Where terminal. This is the external connection points for the capacitor. This is our brief explanation of the power film capacitors. Next, a step-by-step explanation of what is a electrolytic capacitors is based on the below points. An electrolytic capacitor is popularly known as a polarized capacitor, where in the anode has more positive voltage than the cathode. It means an electrolytic capacitor is popularly known as a polarized capacitor, meaning it has a positive terminal means anode and a negative terminal means cathode. In operation, the anode must always be at a higher, more positive voltage than the cathode. If the polarity is reversed, it can damage the capacitor or cause it to fail, sometimes even explosively. They are used in filtering applications, low pass filters, audio amplifier circuits, and many more. Electrolytic capacitors are widely used in various electronic circuits due to their high capacitance values. They are commonly used in filtering applications means especially for smoothing rectified DC in power supplies. Low pass filters means to block high frequency signals and allow low frequency signals to pass. Audio amplifier circuits for coupling and bypassing, helping to block DC and pass AC audio signals. Timing and delay circuits, motor starters, and energy storage in pulsed systems are other common uses. Their large capacitance makes them ideal for handling bulk energy storage and signal conditioning tasks in electronic systems. Metals like aluminum, tantalum, niobium, manganese, etc. form an oxide layer in the electrochemical process, which blocks the electric current flowing in one direction but permits the flow of current in the opposite direction. In simpler terms, certain metals like aluminum, tantalum, etc. are used to make electrolytic capacitors. During manufacturing, these metals undergo an electrochemical reaction that creates a very thin oxide layer on the metal surface. This oxide layer acts like an insulating dielectric. It prevents current from flowing backward. However, when the correct voltage polarity is applied, anode more positive than cathode, the capacitor functions normally. If the polarity is reversed, the oxide layer breaks down and current may flow in the wrong direction, potentially damaging the capacitor. Electrolytic capacitors uses an electrolyte to operate with a higher or more positive voltage on the anode than on the cathode. It means electrolytic capacitors are polarized and designed to operate with a higher voltage on the anode, means positive terminal, than on the cathode, means negative terminal. This polarity is crucial for their operation and is determined by the asymmetrical construction of the capacitor. Reversing the polarity or exceeding the rated voltage can damage the capacitor. Therefore, the anode terminal is denoted with a positive sign while the cathode with a negative sign. In simpler terms, electrolytic capacitors, the terminals have fixed polarity. The anode means positive terminal is marked with a plus sign. The cathode means negative terminal is marked with a minus sign. This labeling helps ensure the capacitor is connected in the correct direction in the circuit. Connecting it the wrong way can damage the capacitor due to its polarized nature. Applying a reverse polarity voltage of 1 to 1.5 volts may destroy the capacitor and dielectric, and the result is hazards leading to an explosion or fire. For this reason, the polarity is marked on the device housing. Applying a reverse polarity voltage or a voltage exceeding the maximum rated working voltage of as little as 1 or 1.5 volts can damage the dielectric, causing catastrophic failure of the capacitor itself. An electrolytic capacitor uses an electrolyte in the form of solid, liquid, or gel, serves as cathode or negative plate to achieve much higher capacitance per unit volume. It means an electrolytic capacitor uses a special chemical called an electrolyte, which can be solid, liquid, or gel. This electrolyte acts as the negative side, means cathode of the capacitor. It helps the capacitor store more electric charge in a smaller space, making it useful in many electronic devices. On the other hand, a positive plate or anode made of metal acts as an insulating oxide layer formed through anodization. This allows an oxide layer to work as the dielectric of the capacitor. In simpler terms, the positive plate of electrolytic capacitor is called the anode. It is made from a metal, usually aluminum or tantalum. A very thin layer of oxide, an insulating material, is created on this metal surface by a process called anodization. This oxide layer acts like the dielectric, which is the insulating part that stores energy between the two plates of a capacitor. Next, we discuss about the advantages of electrolytic capacitors. First one, high capacitance. It means they can store a large amount of electrical charge, even a small sizes. Second one, low cost. It means they are inexpensive and widely available. Third one, good for filtering and decoupling. It means they are great at removing noise from power supplies and stabilizing voltage in circuits. Fourth one, can handle large currents. It means they can work with high current levels, making them useful in power supply circuits. Next, we discuss about the disadvantages of electrolytic capacitors. First one, limited lifespan. It means they don't last as long as some other capacitors, especially in high temperatures. Second one, leakage currents. It means a small amount of current can leak through them even when they should be blocking it. Third one, polarized. It means they must be connected the right way, positive to positive terminal and negative to negative terminal. Wrong connection can damage the circuits. Fourth one, equivalent series resistance. It means they have some internal resistance which can reduce efficiency in high speed circuits. Fifth one, temperature sensitivity. It means their performance can change with temperature, especially in extreme heat or cold. Next, we discuss about the applications of the electrolytic capacitors. First one, power supplies. It means electrolytic capacitors used to smooth and filter the output voltage. Second one, audio amplifier. It means electrolytic capacitors help to block DC and pass AC signals, improving sound quality. Third one, flash lamps. It means electrolytic capacitors store energy and release it quickly to power camera flashes or other pulsed devices. Fourth one, coupling signals between amplifier stages. It means electrolytic capacitors are used to transfer AC signals from one stage to another while blocking DC. Fifth one, medical devices. It means electrolytic capacitors provide stable power and support for sensitive electronics like heart monitors. Sixth one, renewable energy systems. It means electrolytic capacitors are used in solar inverters and wind power systems for energy storage and voltage regulation. The image displays the internal components of an electrolytic capacitor, which is a type of capacitor commonly used in electronic circuits, where anode and cathode, they are the two conductive plates or terminals of the capacitor, with the anode being positively charged and the cathode being negatively charged, where dielectric. This is an insulating material placed between the anode and cathode. In electrolytic capacitors, this is often an oxide layer formed on the anode and also includes the electrolytic paper, where electrolyte. This is a conductive liquid or gel that provides the necessary ions for the formation and maintenance of the oxide layer, which acts as the dielectric, where oxide layer formed by air. This thin insulating layer, typically formed on the anode, acts as the primary dielectric material that stores the electrical charge, where electrolytic paper. This paper is impregnated with the electrolyte and helps to separate the anode and cathode while providing a medium for the electrolyte. This is our brief explanation of the electrolytic capacitors. Next, a step-by-step explanation of what is paper capacitors is based on the below points. Paper capacitor is also known as a fixed capacitor, in which paper is used as a dielectric medium that stores energy in the form of the electric field. In simpler terms, a paper capacitor is a type of fixed capacitor. It uses paper as the insulating layer called the dielectric. This layer helps the capacitor store electrical energy. The paper is placed between two conductive plates to form the capacitor structure. These capacitors are used at power line frequency with a capacitance value of 1 nanofarad to 1 microfarad. It stores a fixed amount of electric charge. It means paper capacitors are used in circuits that run on power line frequency like 50 or 60 edges. They have a capacitance between 1 nanofarad and 1 microfarad, and they store a fixed amount of electric charge. In simple version, these capacitors work in power circuits and store a set amount of electricity. A paper capacitor is made up of two metallic plates with a dielectric material, paper between them. It has positive and negative plates. In simpler terms, a paper capacitor has two metal plates. Between the plates is a layer of paper that acts as the insulator, means dielectric. One plate is the positive side and the other is the negative side. The paper layer lets the capacitor store electric charge between those two plates. When a small amount of electric charge is applied over the plates, the positive charge is attracted to one plate and a negative charge is attracted to another plate. It means when a small electric charge is applied to a capacitor, positive charge move to one plate. Negative charges move to the other plate. This creates an electric field and the capacitor stores energy. In simple version, when electricity is given to a capacitor, one side gets positive charge and the other side gets negative charge. This is how it stores energy. This electrical energy is stored in the form of the electrical field. This stored electrical energy is used by the discharging of a capacitor. In simpler terms, the electrical energy in a capacitor is stored as an electrical field between the plates. When the capacitor is discharged, the stored energy is released and used in the circuit. These are available in the range of 500 picofarads to 50 nanofarads. In simpler terms, these capacitors come in small sizes from 500 picofarads to 50 nanofarads, depending on how much charge they need to store. Next, we discuss about the advantages of the paper capacitors. First one, fixed capacitance. It means paper capacitors store a set amount of electric charge that doesn't change. Second one, high voltage handling. Paper capacitors can withstand high voltage without breaking. Third one, reliability. Paper capacitors work consistently and stably over time. Fourth one, cost effective. Paper capacitors are inexpensive to produce and use. Fifth one, design flexibility. Paper capacitors can be made in different sizes and shapes to fit various needs. Next, we discuss about the disadvantages of the paper capacitors. First one, moisture absorption. It means the paper can absorb moisture from the air, which can damage the capacitor or reduce its performance. Second one, drift in value. It means the capacitance may change over time, making it less accurate. Third one, aging. It means paper capacitors can wear out with time, reducing their reliability. Fourth one, high dielectric losses. It means they lose more energy as heat compared to other types of capacitors. Next, we discuss about the applications of the paper capacitors. First one, power conditioning. It means power capacitors used to stabilize and smooth power supply voltages. Second one, car audio. It means power capacitors helps in improving sound quality by filtering and separating signals. Third one, sensors. It means power capacitors used in electronic sensing circuits for accurate signal detection. Fourth one, filtering and coupling. It means paper capacitors removes unwanted signals and passes signals between stages in electronic devices. Fifth one, signal processing. It means paper capacitors helps manage and shape signals in radios, TVs and communication systems. This image shows the working principle of a paper capacitor, where plates means conductors. There are two conductive plates, one becomes positively charged means plus symbol and the other negatively charged means minus symbols. Where dielectric material means paper. A paper layer acts as the dielectric material between the plates. It prevents direct electron flow between plates and stores electric energy. Where current flow top to plate. When a voltage is applied, current flows into the top plate. This deposits positive charge on the top plate. Where electron flow bottom of the plate. Electrons are repelled from the top plate and accumulate on the bottom plate, creating a negative charge. This is shown as electron flow upward from the bottom. A paper capacitor stores energy by accumulating opposite charges on two plates separated by an insulating paper dielectric. Current causes charge build up and the dielectric prevents flow, enabling energy storage. This is our brief explanation of the paper capacitors. This is our concept of the different types of capacitors. Thank you very much. Padmam Himam.